what I wanted to do today didn't work out, okay? And I didn't have time this morning to fix it because I was stuck in traffic coming back from vacation, okay? So we'll just have to improvise some things here, okay? And hopefully learn something still, okay? So one thing I thought I would do is go back and think about the pi calculus, but this time see if you can give some kind of operational semantics for it, okay? As a forward chaining logic program, the way we have been thinking about substructural operational semantics, okay? So we wrote down the linear lambda calculus and we gave a substructural operational semantics for it, and we were able to implement it in CLF and we're able to run it. And there was a small bug there, okay, but I fixed it, okay. So the code that's online, I think, had that small bug fix in it, okay. And the basic problem was that in the informal presentation, we made a very strong distinction between unrestricted and linear destinations. When I actually typed it in to CLF, I called them both just destinations, and that created some interference between the rules. Rob, you have any comment on that? Okay, okay, okay. So, so the question is, can we use the same technology to go back to the pi calculus and maybe give some semantics for it? And then also figuring out, you know, what these kind of strange structural congruences that we had that we kind of needed earlier, what they actually are. You know, what does that mean actually? Okay, so let's just get started. So one of the primary constructs of the pi calculus is parallel composition, right? I mean, that's basically how you get parallelism. So the question is, if you have a predicate eval, and it takes a process expression as an argument, okay, how does P in parallel with Q evolve? Okay, so what does eval, how do you actually, now, previously eval took two arguments, so just a reminder. So eval took a term m and a destination, say, x, okay? And the idea was somehow evaluate and communicate your value along channel x or to destination x. And then we had return of a value to a destination x. And we also had a continuation, which was taking input along one. Then we had some frame here to do some stuff and then pass the result to w. Okay. So now in the pi calculus, I'm going to try to do this differently. And the way I'm going to try to do it differently is not have destinations. Okay, so not have a third argument. And somehow, because they're already built into the calculus, okay, because we already have channels, okay. So a process doesn't necessarily have to have a channel as the destination because it doesn't produce a value, it just computes, okay. Okay, so evaluation in this case, so that was last time. Evaluation just takes a process expression P as an argument. And we'll see what else we need. Okay. So the way to picture that is that these things are part of your context, right? And we're trying to describe the state change that takes place when the computation happens. Okay. So what would be the state change for evaluating P and Q in parallel? Yeah?
We have both of them to the context?
We have both of them to the context, right?
Evaluation's over.
Right. So we have to evaluate P and we evaluate. Okay, does that make sense? So our goal is to evaluate P in parallel with Q. And now we have P and Q both in the context. Now they can each individually evolve, right, independently. If you have a rule that applies to them, they can go. So we get that kind of concurrency from the fact that after this step, there's going to be multiple evals in the context. Each of them could be subject to a forward chaining rule. Does that make sense? Okay. So just from this one rule, previously we had this kind of thing. P parallel Q is structurally equivalent to Q in parallel with P. Okay. What does it actually mean now here? Yeah, so that actually is because, so A tensor B is equivalent to B tensor A. Or if you think about it as a property of a context, once we have fired this rule, what property of the context would that be? The exchange, the order doesn't matter. Order of linear hypotheses or linear resources is irrelevant. So another way to say that would be like A comma B is in some sense equivalent to B comma A, and we use that only for eval. Okay? Okay, pretty simple. So another way to say this, if you will, is that parallel composition is just tensor. Okay, let's see how far we get with that. How would you evaluate the terminated process that can no longer interact? Yeah, but how do you say nothing? I can't just write nothing here. 1. So another way to say is 0 equals 1. Okay. We shouldn't probably build a whole mathematical foundation on that, but okay, at least so far. But it just disappears, right? If you evaluate 0, you do the transition, it's gone. Okay? So let's think about name restriction. If we have eval of nu x p, okay, so we used that in several places. We used it in cut in order to create a private channel between the two pieces that were communicating. We also used it in output in order to create a new name to output. Okay. So how does this work? Yeah, louder?
There exists an X,
Okay, there exists an X that we can evaluate P. Okay, yeah?
Well, yeah, P has to have some knowledge of X.
Okay, so this P actually can depend on X. Okay, and so since we gave it the same name, we'll just use the same X here. Or we could say this is a Y and this is P where Y is substituted for X. Okay, don't have to be the same name, but okay. Okay, so what does that actually mean operationally? When you come and you see nu of x dot p of x, right? What does it mean as a state transition? Well, we introduce a new name, which is what the left rule for the existential does. We put it into our context psi, and we continue to evaluate underneath that. Okay, is that the right interpretation for that? Okay, not as obvious as this one here. By the way, let's look at a few other congruences here. If you have P in parallel with 0, that should be equal to P. So how do we get that? Okay, all right. If you take A tensor 1, it's equivalent to A. I'm not sure if there's a good way to say it in this way, equivalently. Okay. Okay, so what happens with the existential? So remember we have this law of scope extrusion, right? Okay. So let's write that over here. Okay, so we have P in parallel with nu x q, then this is equivalent to nu of x, P in parallel with q under some assumption about P, which is x is not in the free names of P. Right, so we can widen the scope, okay? And that's okay as long as this doesn't depend on x, okay? So what's happening with this rule? Related to that. Right. But there's a scope extrusion when that happens. Where's the scope extrusion take place? So we have in our context a whole bunch of evals, right? A whole bunch of processes which we all got by taking something that's parallel and decomposing it into the pieces, right? There's an eval of P, and there's an eval of nu of x dot q after we break down this. Now we introduce a new parameter, we move it all the way to the outside and add it to psi, and thereby include P in its scope. Okay. So by moving the existentials all the way to the outside, we kind of built in this rule of scope extrusion. Okay. So at least going from here to here, where the scope is actually extruded, the scope of x is wider than it was before. Okay. Okay. All right. What other constructs do we have? Okay. So let's do input. So we input. Okay. So we input a y along x, and we have p, which can depend on x and y. Okay. So what do we do for that?
Can't evaluate this until you have a corresponding places ready to give it to you. So.
Correct. So we need some, yeah?
So I guess you could, well, you could either create some other extra construct, or you could just require that you have a second eval that takes that, that provides that.
Okay, so either we have to have a second eval that kind of can synchronize with this one, or we can evolve to some construct with just a synchronization. So in the spirit of the substructural operational semantics that we had before, we have evaluation as kind of asynchronous. When you see that, you can always fire.
Okay.
And if something has to wait, then it's going to be like a return or a continue. Okay. So we're introducing a new construct here. So I guess let me call it, let's see, input. And what's the argument? I guess the first argument should be the channel along which you input, and the second argument should be the scope. Okay. So y is a bound variable here, and pxy is its scope, and I've isolated the channel along which I expect the input to the outside. Okay. Okay. Obviously, the next thing to do is the output. So if I evaluate and I output some y, and then I have some p, which depends on x and y. Okay. Then I want a new construct out. Okay. And this time I'm going to give it three arguments. Okay. The x, the y, and the p. Okay. Because now it's separated from the scope. X, y, and some p, which depends on x and y. Okay. So at some level of approximation, you can think of input like being a return, so to speak, and out being like a continuation. But you could also think about the other way around, because communication is a little more symmetric here. So I didn't want to reuse the names return and continuation, because here it's not really clear what you return and what is a continuation. Okay. But we do need a rule now for the two to interact. Okay. So what would that rule be?
We have an input along the channel and an output along the same channel, then we can just do substitution.
Okay. An input along a channel and an output along the same channel. Q of, oops, y. Yeah, so I think I probably write it like this, because there's no bound variable here except y. So x and y are like free variables here. Okay. Okay, so I have q here. Okay. Okay, so what do I generate from this? I want to substitute, which was correct. So what do I substitute for what?
Z in for y and p, and then you evaluate those in parallel.
Okay, so I have p, and I substitute z for y. So the result now depends on z where it depended on y before, and I evaluate that. And I evaluate that in parallel with q. Is that right? Yeah, so actually come to think of it, in this rule here, x is not really a bound variable. So, of course, x can occur in here. But if I just indicate dependence on bound variables, it would only be on x. So you wouldn't have that here. Okay, so we have a dependence on the bound variable here, which is y. And we take that and we replace z for y, so the result can now depend on z, but the bound variable is eliminated. Okay, does that make sense in the interaction rule? Okay, so it's sort of like what we had before with the return and continue. Okay. Do we need to do anything else? Forwarding, okay. So what do we do with forwarding?
I mean, couldn't we just expand forwarding out into like the component definitions that let you do forwarding down until you get to your base type and then evaluate it that way rather than bothering to write a separate rule for it?
Okay, I like that. Okay, okay. Sort of eliminate it by definition. Okay. And in fact, in the pi calculus, usually there is no forwarding construct, okay, because it can kind of be implemented, okay. So one implementation would be something like, xw is defined as either you input a y along x and then you output y to w and then you terminate in parallel with or wy, and then you output y along x, and then you terminate, okay? And if you don't do any typing, this kind of thing, this kind of thing seems reasonable, okay? It's the typing, okay, that makes this kind of thing tricky, which is why we hit the forwarding construct as a primitive, okay? There's also some issue here with this kind of definition, which is that once, let's say, this part actually forwards from x to w, okay, then this thing we kind of hang around as junk, okay? And you see a lot of encodings of things into the untyped pi calculus. They have this kind of junk hanging around as part of the evaluation. It's nice not to have to worry about that in the typed case. But if you want to do, generally speaking, if you want to do the untyped pi calculus, we wouldn't have a primitive forwarding construct, but we would expand it to whatever we need in the particular context. Now, another way to do it would be to have a new thing called, let's say, forward, okay, and then a bunch of rules that describe how forward interacts with input and output, right? So that would be completely explicit about it, okay? So that would be something like, well, you can probably imagine what it would be. So you evaluate x w goes to forward x w, okay, and then you would have a rule that might say something like if you have an output on x to z followed by p together with the forward xw, then you would take an output on w, z, p. You might have something like this. These two kind of definitions, doing it this way or this way, aren't exactly the same, right? So one of the things that happens here, if you want to output something and this is waiting to forward it, you can actually continue with the rest of your computation, right? Because once this forwarding process has swallowed it up, right, you are free to continue with p, okay? In this kind of definition, okay, you would actually be waiting until there's a real recipient at the other end, okay? Because you're still under some prefix now waiting to output along a different channel than you were you were doing it before. Okay. Another way to think about this is that, I can write it here. If you had some kind of equality in the system, okay, you could just say, if we're evaluating this, let's just equate these two channels. X is equal to W. Okay. And then we'd have to introduce equality, okay, into our language and explain what that kind of thing means. Okay. In this particular case, it's easy to see, even though Rob doesn't want to. Rob is getting a headache. Okay. I have some ibuprofen with me if you need it. Okay. So basically, in this particular case, you can see what happens. You have a psi, and you have an x, which is a channel, and you have a y, which is a channel. And you have some gamma, and you have some delta, and in here you have an x equals y. Okay. And then you're trying to prove some kind of, let's say, a c here. And what this corresponds to is simply replacing x and y with some new z and substituting z for both x and y everywhere in this judgment. Okay, so it corresponds to the transition where you have psi, you have z as a channel, gamma where you substitute z for x and z for y. Actually, I write it only once. Okay, gamma, delta, arrow c, and in this whole sequence, we substitute z for x and z for y. Okay. Let's see. So this would be in the inversion phase, because this equality can always be applied, so there wouldn't be any focus on here. Okay. So I don't want to get into the whole issue of defining equality. Okay. But that's another possibility that one can do. Okay. Okay, it's a little problematic. So the third one, which is actually the original suggestion, is that this kind of forwarding, okay, can be defined in a type-directed way. So forwarding at type A tensor B can be decomposed in forwarding in type A and forwarding type B. And that kind of process is what kind of operations on proofs? Identity expansion, right? Because this is the proof term for identity. So if you have identity at A tensor B, you can reduce it at identity at type A and type B. You can reduce it in the type all the way until you're just forwarding at atomic type. Okay. So that's another way to eliminate that. And then you can say, well, we don't really have atomic type, so then it just goes away in the end. Okay. I guess the other thing to worry about is bang, though, right? So how do we do that? So how do we evaluate bang P? Or maybe we shouldn't do that. Actually, we didn't have bang P. What kind of bang did we have? Replicated input. So how would we do that? Yeah?
So it would seem natural to have that go to an input, as we had before, and then it's kind of mirroring what happens in
Okay.
a tensor, and then we want to keep it around. But then we duplicate it.
Okay, so we have an input, okay, and we duplicate it. Now the problem with this rule is yeah, right. This rule can fire spontaneously, right? Arbitrarily often. So you can flood the context with arbitrarily many copies of the replicated input. Okay. So it would be nice if we didn't have to do that, right? If replicated input was sort of working on demand the way it was working in our semantics. So how would we do that?
Just put a bang in front of the bang.
Yeah. Just do it like that. And then we don't need that. Okay. Okay, so we just have a replicating input there. Now, does that actually work? Let's see. If we need an input here because somebody wants to output to that channel X, can we use that in order to satisfy this goal here?
Yes.
Yes? Okay. Because?
A persistent resource can satisfy the requirement of the one.
That's right. And in focusing terms, input is positive, and we're going to be focused, when we focus on one of these rules, right, we're going to be focused on the right on this. So our goal is going to be input of x, y dot p, which depends on y, where this is positive. Okay, and we have to look in our context whether there's something that matches that. Okay, now there's two rules for positive atoms. Okay, one is it's in the linear. It's the only thing in the linear context. That's for the ordinary case if we had an input somewhere that'll match that. Okay, but we can also look in our unrestricted context gamma. Okay, and that will happen if there was some kind of evaluation of a persistent input, of a replicating input before. And so it's perfectly okay if we have that input x, y dot p of y here in the unrestricted context as long as this is empty as part of the focusing. And there's going to be some other stuff here, of course. Okay, like that. Okay, so it works out because we have more than one. We have two rules. When you're focused on the right on a positive atom, it could either be in here or it could be in the unrestricted context. And so therefore, this is okay. And in fact, Milner says something in his paper when he introduced the pi calculus about choosing the bang notation when he wrote this. Okay, he said something like, well, using the name notation as we do in linear logic is no accident, even though I don't know the precise relationship between those things. Okay. So here they turn out to be essentially the same thing. So we can kind of give a logical meaning to the constructors of the pi calculus, right? So the logical meaning of parallel composition is tensor, of 0 is 1, okay? Of name restriction is existential, okay? And then input and output, we don't have any direct logical reading, okay? At least not in this form. And replication turns into, well, persistence. Okay. I guess we should think about choice because we had that x dot in left and case. So we should complete the picture just to see what happens with those things. Okay. Okay. So evaluate x dot case p comma q. So how do we do that? Well, we have to wait before we can do anything, right? Because we have to communicate with somebody. What are they going to send us? In left or in right. Okay. So if you want to reuse this kind of thing, right, we would not do an input or output. Well, actually, we would do an input, right? Because we're waiting for somebody to send us the choice. So it would be an input, waiting on x. And then we would have to do a case between P and Q. Okay? All right. So if we're actually sending x dot in left followed by P, what would that become? well, it would do an output, right? Out. On X, what would we send? Well, let me just write it in left. And then we would continue with P. Okay? So now we need one more interaction rule because, well, the other possibility, if this is in right here, then we would have an in right here. Okay? And so we need one more rule for interaction. What is it? Or actually two more rules, right? So what does it look like? Case PQ. And you have an output on this channel X of a, let's say, in left. Continue with R. Okay. And what do we go to? Eval P and evaluate R. Okay. Okay, we also had this thing with 0, with the 0 area input for 1, but let's skip that. Okay. So does that make sense as a semantics? Yeah?
So wouldn't we have to choose some other predicates for that? Because there's something with the types here that seems off.
Yeah, so the question is, what is the first argument? The first argument of input and output is a channel. That's consistent. A second argument should be a message. And a message can either be an in-left or an in-right or a channel. Okay. And the third argument of an output should be a process, which is okay. The second argument for an input should either be an abstraction or a case. So we need to create some of these types in order to make typing work out for this. Or you can create new predicates, but I prefer to keep the number of predicates small and just trying to, because in fact it is a communication that happens with the case. So I just like to make that explicit by reusing the same predicate. Yeah. Okay, other questions? Okay. All right, let's think a little bit more about sort of the forward chaining model of computation. Okay, because we need to a little bit understand better about when it is appropriate to think about it this way and when not. Okay, so okay, can I go to this? The questions before I erase that? Okay. Okay. So in Bloch's world, okay, we had a rule like this. If X was on Y and X was clear and the hand was free on empty, then you could transition to, okay, state where Y was clear and the hand holds X. Okay, and in fact, the only other rule that we had was the same thing going in the opposite direction, right? If we're holding X and Y is clear, we can put it down, which means now the hand is empty, X is clear, and X is on Y. Okay. So now if you take those two rules together as a forward chaining logic program, okay, are we done? Have we programmed Bloch's world? Okay, first to note, it's an hour fragment of which we can do forward chaining. If all the atoms are positive, right, there's no problem here. It's actually a very simple thing. The problem is that basically the thing will never terminate, right? Because the rule can fire. You can, essentially no matter what your initial situation, as long as you have one thing that can be picked up, you can pick it up, put it down, pick it up, put it down, and so on, right? So if termination is defined by you cannot make a step, okay, these two rules together give you an infinite cycle, okay, and it will never actually terminate. So it serves perfectly well at describing a system of state change, but it doesn't work very well as a forward-chaining logic program, because as a program it will never terminate. Okay. So when we write programs, we always have to worry about the fact whether they terminate or not. Okay. And in fact, if you think back, do these programs terminate? For example, does our eval return cont semantics for the linear lambda calculus, does that terminate? Okay, and why does it terminate?
You can go back from return to it all instantly.
Okay, but so the question is, how do we know that if we start in some state and we have to evaluate the term m with some destination x, then after a finite number of steps, we can generate a return. So how do we know that this always terminates?
Depends on whether M is closed or not.
Okay, potentially depends on whether m is closed or not, or if it's not closed, what things it depends on. Okay, so let's just say, for simplicity, this. Okay, so how do we know this? Yeah?
Well, so depending on what the lambda calculus language is, if we can construct a fixed point, then it's not going to terminate.
Right. So it depends exactly on which terms we allow. So in the linear lambda calculus, if m is well typed, okay, then in fact there's a theorem that says that this will always terminate, but we actually have to prove that. It's not a triviality at all. It's a hard theorem, right? So it's good as an operational semantics if you want to allow non-terminating programs, because then our forward-chaining program also doesn't terminate. Okay? But if you want to show that it terminates, we have to prove a property about a particular system that we wrote down, and that's a hard theorem. Okay? So in this case, it turns out to be somewhat related to cut elimination. Okay? The fact that cut elimination always terminates. You can apply a similar argument to show that if m is well typed in the linear lambda calculus, then in fact you cannot construct a fixed point and all evaluations will terminate. Okay, but that's a theorem that we haven't proven. Okay, okay. Certainly in the pi calculus, okay, because we weren't typing it, in the untyped pi calculus, evaluation might not terminate, so we could have infinite chains of reductions and computations. Okay, and so we can here. So if you want to actually take these things and run them to get an observable answer, okay, then this kind of thing is not a good program. It's good to describe very concisely how Bloch's world operates, okay, but you can't really run it directly. So if you really want to run it as a program, you need different techniques. You need different encodings. Okay. But some of the things that we have done actually do constitute good programs. Okay. So the one example I want to do for that is the spanning tree example. Okay. Okay, so can anybody remember how the spanning tree example worked? So we had some predicates. We had node, which x, y, g. X and g, which said that x is a node in graph G. Okay, and we had edge, x, y, g, which said that in graph G there's a node from x to y. Okay, is it coming back? Okay, all right. So how did this program work? There's only two rules. We should be able to reconstruct those, right? Initially, we pick one node. So we have some kind of linear thing called init together with a node x, which is in the graph G. And we move it into the tree, and how do we represent that? Yeah, so node x. I'm going to write T for the tree, so G is the graph and T is the tree. So now X is a node in the tree, and this fact is consumed, so this rule can fire only once. Okay. Now what's the second rule? So you have to remember how this... Okay, so we have a node X already in the tree. Okay, and we have an edge from X and Y, which is still in the graph G. Okay. And Y is still in G. Okay, then? And node Y is added to T. Okay, one more thing. X is still in T. Okay. Okay, now there was one more thing here that we have to worry about. The graph was undirected. How did we do that? Edge x, y, g goes to edge y, x, g, except this g is different, so let me write h when it's a variable. Okay, so for h, either t or g, the thing is undirected. Okay.
Not really needed for T, right?
Hmm?
We don't really reorient.
Yeah, we don't really need it for t. Okay. So if you wanted to, we could just say, okay, just for this particular graph G, this is going to be the case. Okay. Okay, so the first two rules are pretty promising, right? Previously, we argued that this would actually, something would decrease every time, and some other things would remain invariant. So what would decrease here every time you apply this?
Nodes in G?
The nodes in G, because every time you apply this rule, except for actually the first one too, take a node out of G, add it to T. You would take a node out of G and add it to T. So the number of nodes in G goes down by 1. If you have finitely many nodes in G, you can only at most do n steps, where n is the number of nodes in G. Okay. So these two here are good because they're bounded by the size of G in terms of the number of nodes. Okay. Now the last one is problematic, right? Because that would fire arbitrarily often. Okay. And so this would not terminate as it's written. So the question is, how do we fix that? Say that again. So another premise here.
I think the previous row.
Oh, this one here? What? Oh, okay. So we make a copy of the previous rule, and we just add x, y, x, g. Okay? Everything else stays the same. Okay, and then we throw away this rule. Okay, so that's a nice solution, right? Okay, Rob, can anything else occur to you?
We could make edge persistent.
Okay, we could make edges persistent. Okay, so let's think about that. So if you make edges persistent, then we could say this here. And we could take this here. And, oh, these are the only place where edges. And then how do you specify the symmetry? Well, let's say if I have an edge from x to y in h, then I can get an edge from y to x in h. Okay? Okay, so that doesn't seem much progress because this rule can fire infinitely often too. Okay? So we have to change our operational semantics to account for that. Okay? But the change, fortunately, is a standard thing. Okay? So what we want on the linear resources that we have is called quiescence. So you can take no step that would add some new linear resources. On the unrestricted resources, we want something called saturation. Okay? And saturation means that, so saturation means that you cannot fire any rule that adds something new to the context. Okay?
No, the other way
Hmm?
around.
You're such a...
You can't fire any rule that doesn't have.
Okay.
Add something not
That adds only things that aren't new.
Right.
You can only fire rules
That add something new.
unless they consume linear resources. So it's actually
Right. Okay. So if we only have unrestricted things, okay, then we have reached saturation if no matter which rule we fire, the facts that we would derive are all already there. Okay. So that's saturation. So we're kind of saying at this point there is no reason to continue firing the rules because we already know everything that we're going to know. And that makes sense for the unrestricted context because those pieces of knowledge are persistent. Okay. So there's no reason to learn the same thing multiple times. Okay. So in fact, there's a whole class of logic programming languages that are based on that come from something called data log, okay, where you actually do bottom-up logic programming inference, and you stop when there's nothing new that you can derive. Okay. And there's applications for that in like network routing and many other different types of applications. Okay. Now, so that's saturation. And on the other side, when we do something purely linear, we have quiescence. Okay, which says that if you forget about the unrestricted part, that no rule can fire. Okay, because either the context is empty or it only has a return in it with nothing waiting on X. Okay, we have reached quiescence because no rule can be fired. Okay, so now we have to try to combine these two. Okay, and okay, what's the simplest way to say this? So let me write down what I think, the way I think about the operation semantics in case you have both of these. Okay. So you have a gamma and you have a delta initially. Okay, let's call these gamma 1, delta 1. You make a transition to gamma 2, delta 2, and then you continue. Right? That's the naive model that we have in our computation. And for example, we always know that gamma 2 is some kind of extension of gamma 1, right? Delta 1 could be unrelated. Gamma 2 is always an extension because we never forget what we already know. Okay, so we can proceed that way. Okay, and in fact, we might as well add the last thing here if we want, psi 1, and then we get some kind of psi 2 here. Okay. And we continue with the computation. We also know that psi 2 is some kind of extension of psi 1 because, huh? Unless we add equality, it's always some extension of what we already know. Okay? Okay, so now we have to define when we have reached quiescence. Okay? By the way, one of these, if you remember, this arrow here, transition arrow, means that we focus on some assumption in our context and play through the two phases of focusing and inversion to the conclusion, and then we get something that looks exactly like what we had before. Okay. Okay. So what do we want to say at this point? When do we have a final state? So I'm tempted to say that any rule that we fire gets us back to the same state.
That's slightly different though,
Okay.
because if you have A linearly implies A, then you'll finish the cycle at that point. That's okay, but that might not, I don't think that's what we normally mean by classes.
Okay. Okay. So that idea was too naive because probably our operation semantics would not discover this, right? It would just, if you have a rule like this in your program, it would cycle forever, right? Okay. Okay, so the way that Rob and I worked on this before is that you don't actually interleave these rules arbitrarily, okay? But you actually divide the operation semantics into phases, okay? And sort of there's one phase where you saturate gamma 1 all the way until what condition, Rob? So you fire rules that have no linear premises, right?
Or linear conclusions.
Or linear conclusions.
You fire completely nonlinear rules
Oh.
until you can't derive anything new.
Okay, so we start by applying this many times, okay, and delta stays the same, okay. And we get some new gamma 2, and the gamma 2 is saturated, ignoring all the rules, except the ones that go from unrestricted to unrestricted, okay. So now we have all the consequences that we can get in gamma 2 without changing the linear part of the context, okay. Okay, and now we can select some other rule, okay, or not. If there's no other rule we can select at this point, then we stop, and we're finished. If there's a rule that can fire that can, at this point, which is mixed linear, nonlinear, then we do that, and we get some new state, psi 3, gamma 3, delta prime, and then we repeat the process by saturating gamma 3. Okay, so that's kind of was the best thing we'd come up with. And it seems like a reasonable thing. Okay, and it would work in this case because in this case, what you basically do is sort of at each step you make sure that your edge relation remains symmetric. Okay, and actually, after you add an edge to the tree, okay, you actually have to resaturate and make the edge relation in the tree also symmetric, which is what you really want intuitively because these are undirected graphs, undirected trees. Okay. Yep.
So if we make edge persistent,
Yeah.
then that's kind of weird because there isn't even nodes. Like nodes are not persistent. So then we will have a graph which, like there are edges, but not linear.
Right.
Isn't that kind of weird?
Yeah.
Or there are lots of graph algorithms where you don't change the graph, but you recolor the nodes. And so I would say that that's all we're doing here. We're recoloring nodes.
Yeah.
Like we're using node to stand for the fact, like, we're using node to like stand for the fact that not process this node.
Well, yeah, but then we perhaps could use some other.
Yeah, very clear.
Yeah. So, yeah. So it's okay. It was easier not to invent some new name, but I think it's a valid point. Yeah. Okay. So if you make this change to the operation semantics, then even this version where we make sure that the edge relation remains symmetric at each point in time terminates. Okay. And basically, the macro phases are bound by the number of nodes that you have, because that's how, at most, how many rules you can fire. And in each step, there's a little bit of saturation going on in the sense that you have to make sure that the edge relation is symmetrically closed. Okay. Okay. Okay, so this is something that actually is a valid algorithm that you can run as a program, while something like the blocks world is a specification of how the system can evolve, but it's not a program yet. So if you wanted to turn this on the program, you need to do something else. Okay. Now another point about this is that the way we think about the operational semantics is don't care non-deterministic. What that means is that if you can fire a rule, fire it, don't look back. Okay. So we never change our minds when the rule has been fired. So that is the right semantics, for example, for the pi calculus, which we think about the same way. You think about this, interacting processes. If there's multiple interactions that can take place, one of them takes place. Now we change state. The others are no longer possible because we have moved to a new state. Okay. The same thing for the operation semantics here. If there's non-determinism, they can fire in some arbitrary order. We're not going to look back and say, oh, we could have gotten a value if way back then we would have made a different choice. So there's no backtracking in this kind of operational semantics. Another terminology for this is a committed choice language. Okay. So this means that your program is correct only if, no matter how the rules fire, it always gives you the correct answer. Okay. So there is a possibility of more than rule fire. You have to make sure that it doesn't matter which one fires. You always get a correct answer. So in this particular case of the spanning tree, if there may be multiple rules that can fire because the precondition might be satisfied by multiple nodes, okay? And it turns out no matter which one fires, you will get a spanning tree in the end, okay? You will get different spanning trees, you have different outcomes, but each of them is in fact a spanning tree, okay? Okay, so if you wanted to fix this example here, okay, and wanted to always terminate, okay, one thing we could add here at the beginning is moves of successor of n. So we're allowed n plus 1 moves. And then over here we say, at this point we're allowed n moves. Okay? If we're reading it from there to there, and there's a tensor here, right? And then we have to give it some initial budget of moves. Every time the rule fires, right, we decrease the number of moves by 1. And eventually we'll hit 0, and we can no longer make any move because move of 0 will not match this precondition, right? And so now this program will always terminate, but it's still an incorrect program if you wanted to search for a particular solution, at least in this particular case, because you don't know what it's going to do and what the final state is going to be. Okay. So if you're looking for a particular target position, this is still not a good program. Okay. Even though it now describes the possible evolutions of the state with a fixed number of moves in your budget. Okay. Okay, so peg solitaire is in the same class. If you do peg solitaire, where you can jump, we actually know ahead of time how many moves we need. How do we know that?
Count the slots on the board.
Right, the number of pegs minus 1 on the board, right? So if you have 14 pegs, every jump removes 1, so you have, if you start with 15, you're allowed 14 moves, and then 1 is left, okay? But if you make the wrong choice, right, you will not find a solution. So we'll always terminate a block, and you only know if you have a right answer if you end up with being said the number of pegs would be the number of moves if you have 1 peg left. So you have number of pegs, 1 is left. But as a program, it's no good because at any point in time it might make the wrong move. It will never look back. Right? Okay, so one of the next things I want to do in this class after the midterm is talk about backward chaining. Okay, and backward chaining arises from a logical perspective if you take all the atoms which so far we have considered positive, okay, which gave rise to the semantics, and make all the atoms negative. Okay, and then see how proof search proceed. And then you get this thing which is sort of opposite to this forward chaining semantics. And in the backward chaining semantics, it turns out that it's very natural to talk about backtracking in this context. Okay, and then you can write a set of rules that could go down the wrong path and you backtrack and try something else. Okay, you still have to worry about whether your program will terminate and whether you'll always get an answer and so on. But you can express a much richer set of algorithms that way than you can with only forward chaining. Okay. Or let's just say, if you wanted to express them with forward chaining, it's harder to do. Okay, because it's hard to implement this kind of backtracking behavior in a forward-chaining language. Okay, are there questions? Okay, I think I'll finish a little early then today, and wish you good luck on the midterm, and we'll see you next week.